There are many things that we can do with random variables that help us understand exactly what a particular random variable is doing, how it will act, and so on and so forth. And the most common and well-known of all of these things is to calculate the mean, or the first moment of the random variable. The mean is defined as, and we're often going to use the Greek letter mu as the expected value, denoted here by e, which is the integral of a value times the PDF. So what is going on here? Intuitively, the mean is saying what are the different values that a variable can take on, and what is the what is the probability that the variable will indeed take on that value. Then let's add those all up. So in a simple discrete case, we might have a die. No, let's go with something simpler. A three-sided die that can return the value of 1, 2, or 3. I'm not even sure how you'd make a three-sided die, but let's just go with it right now. And the probability of each of these values occurring is, say, 1/2, 1/4, and 1/4. So if we rolled this three-sided bizarre die many times, half the time it's going to come up with the value of 1, and the rest of the time it's going to come up with 2 or 3 with equal probability. So if we did this, maybe we would get a sequence that looks something like 1, 1, 2, 1, 3, 1, 1, 3, 1, and so on and so forth. And as we did this for an infinite amount of time, we would average these values together, and we could sum them all up, and we would have, in essence, on average, we would expect to see n over 2 times 1 n over 4 times 2 and n over 4 times 3. Well, the n's are going to divide out, so we can go ahead and do that. That n, and that n. And we're going to equal, our result is going to be 1/2 times 1 plus 1/4 times 2 plus 1/4 times 3. Now in practice, it's not going to be exactly like this, right? There may actually be a few more 2's than there were 3's just because it's random. So we would have to do this an infinite number of times. As n goes to infinity, we expect the variation to become insignificant. Well, that's exactly what this is doing. In as much as an integral on continuous values is like a sum over discrete values, we have the probability of a 1, the probability of a 2, the probability of a 3, times those particular values, times 1, times 2, and times 3. And that will give us the expected value, or the average value, if we did this over a very long time. Okay, so because the expectations come from an integral, integrals behave very well, when you have finite values and involved. And so the linearity, for example, of the integral means that if we had two variables with the same PDF right now. We'll talk about what happens if it's different in just a moment. The whole thing is linear. We could just factor that out. So in this particular case, we assume they both have the same probability density function. Likewise, notice I've explicitly put in expected value and then x is down below to show that we're using the PDF of x when we do these computations. But because of the linearity of the integral, the a can just factor out. So the mean acts like a linear system. Okay, there's that. What happens now in the case where we have two random variables and they do not have the same PDF, and we want to find the sum, the expectation of the sum of these two random variables? What happens then? Well, this is a little tricky, isn't it? Because the expectation has to be in terms of a PDF, and now we've defined we're asking for an expectation of two values that don't share a PDF. So whenever you see something like this, you just know that under the hood, this is what's going to happen. X plus, we're doing u plus v. There are dummy variables of integration. And p, we're going to have to have our p x y. And so if you have multiple random variables and you're doing the expectation, then we're going to get something like this. Well, how does this work out? On the surface, it's really not too bad. We're going to have the expected value of x plus y is equal to the expected value of x plus the expected value of y, where these are defined in this way. We would do xy, xy, xy. And as I say, most of the time, these values here are implied. We just don't bother writing them down, but it's nice to know where they come from. So it'll be, in this case, u pxy u comma v du dv. And technically these are double integrals. I just was lazy in how I wrote it. So we'll continue with the lazy and just remember, actually that's not best. There. Minus infinity to infinity, minus infinity to infinity, v pxy u comma v du dv. Well, we can simplify this a little bit further. Mainly, this is going to be the integral from minus infinity to infinity of u times the integral from minus infinity to infinity of pxy u comma v dv du. And we've seen this inner quantity before. Recall, this is the marginal distribution of x. or px of u. So now we can go back and actually make a change. We're going to change these subscripts now to reflect that this is now x and that is now y. And the same thing, of course, happens there with the second part, like so. So as a general rule, we can see when we have functions of random variables or combinations of random variables, the linearity still holds. And not only that, we kind of drop these subscripts, because when it comes time to calculating it, we just calculate the expectation with respect to whatever PDF is appropriate for what's inside the bracket. And so everything works out just fine. Okay, next we're going to talk about some special expectations of functions of random variables. And so the next one on our list will be correlation. And the correlation is given by this function, the expected value of the product of the two functions, which of course is going to be p xy uv du dv. So this one doesn't enjoy quite the same simpleness of the expectation or the mean, because in general we can't factor this into two different integrals. We would really like to say that this is equal to the expected value of x times the expected value of y, but in general that's not the case. However, in some very important specific cases it is. So for statistical independence, we've already talked about that. If we have an independent set of random variables, then the PDF's a factor. So let's start with that one. In that case, we would have expected value of xy yielding this expression here, which simplifies to expected value of x times the expected value of y. So once again, that only works for statistically independent random variables, and we get that nice relationship. Just because the means are a product of each other, or I'm sorry, just because the correlation is equal to the product of the means, that does not mean it's independent. So it only works one direction. Independence implies this relationship, but not the other way around. However, even though that's the case, we can also have uncorrelated random variables, and uncorrelated random variables also have this property where the expected value of xy so that's nice. In fact, this is the definition of uncorrelatedness. If expected value of xy is equal to the expected value of x times the expected value of y, then we have uncorrelated random variables. So this implies But that same thing does not imply independence. In fact, it's possible to define two random variables where one is simply the function of another one, and they are uncorrelated, but since one is the function of another one, they are definitely not independent. So a simple example of that would be if we define x to be a uniform random variable on -1 to 1, and y just plain equals x squared, then the expected value of xy is going to be equal to the expected value of x cubed, and this is uniform, so we're -1 to 1, the height of 1/2, u cubed du. Well, that's an odd function over an even interval, so that's going to be 0, which is equal to, actually I guess I should put it right here. Note that this has expected value of x is equal to 0, and the expected value of y is something non-zero. So this indeed does equal the expected value of x times the expected value of y, but it's obviously not independent because they're functions of each other. So knowing one tells you everything you might need to know about the other one. Our next example is that of variance. Variance is closely related to the correlation, and I should probably say I've noticed that people often mix these up. So just as a warning, it's not uncommon for signal processing classes to assume that you have a zero mean random variable. And if you have a zero mean random variable, then variance and covariance can sometimes get mixed up with correlation. So the variance is basically how much we expect our variable to deviate from the mean value. And so here's the definition. But it's also good to note that we can expand this out to be equal to expected value of x squared minus 2 uxx plus ux squared. Now might be a really good time to do a quick aside. Expectations of constant values or non-random variables. That's going to simply be the sum from minus infinity to infinity of c. Well, we really don't have a PDF in this particular case, so you can consider it multiple different ways. Let's just go ahead and throw in any PDF that we choose. This could be any PDF. If you insist on taking the expected value of something, then you postulate a PDF, and I'm going to factor out the constant value, which you can do from an integral, and then it's just the integral from minus infinity to infinity of a PDF, and the PDF is always going to integrate to 1. So that's always a constant. I have a way of visualizing this that maybe comes from watching too many movies, and that is that the curly braces around the expected, the value for which we're taking the expected value, is permeable. If you are a constant of any kind, you can float through it like a ghost. But if you are a random variable, it traps you within. So if that little visualization helps, great. If not, don't post it to Reddit, or I'll be embarrassed. Okay, so there we are. This value right here is just mu x. So we're going to get the expected value of x squared minus 2 mu x plus mu x is going to give us minus mu x. I'm sorry, squared. So here's our other definition for variance, and both of them are useful under different circumstances. Covariance is a lot like variance, except that we are, in this case, finding, it's a little harder to describe what's going on here. We are determining how two variables deviate from their means with respect to each other. And we'll just define this as phi xy, which would be the correlation, minus mu x mu y. This is often called the prediction power, or referred to as the prediction power with mean removed. If we know that two random variables have non-zero mean, then knowing the mean of one and the relationship between the two means tells us the mean of the other, and that's not really telling us anything useful for the most part. So what we really want to know is, as a variable deviates from its mean, is the other one going to do so as well? And in what direction? How are those two things going to be related? It turns out that the covariance is going to be very useful to us in a variety of ways as we develop our adaptive filters. Because adaptive filters are all about what can one signal tell us about another signal, and how can we use that covariance, that relationship between the two signals, to predict one from the other. So we see this a lot. As I'd mentioned earlier, we have this little gotcha in that we often assume zero mean random variables for a variety of reasons. In that case, the covariance will equal the correlation. And so sometimes we use those terms interchangeably when we have a zero mean random variable. But formally, they're not defined that way.